Hello, very good morning to all of you. I'll quickly give you the glance for ITER. Yes, we have the slides. So we are the fusion projects and one of the biggest one in the world right now, and the first one at this scale. To give you a quick overview, and then my other colleagues will take care for the specific procurement and other aspects as well. So ITER, to start with the good news, we recently received this Net Zero Industry Act, got approved in European Parliament, and fission and fusion were the part of it. Fusion actually started really early, but the first actual discussion started between Michel Gorbachev and Ronald Reagan in 1985, which was really fusion. And it started since then, and it took a while to come up with a proper organizational thing. Why fusion? Why we need to go for fusion? First thing first, we all are talking about climate change. It is one of the biggest concern, and energy production is basically one of the largest contributor to the climate change or the carbon emissions. So somehow we need to decarbonize this energy production, and fusion could be one of the answer to that, along with nuclear as well. So it is one of the low carbon source and a promising source for the long-term application for decarbonization of energy. And compared to the conventional fission reactors, we don't have any solid long-term spent fuel or waste coming out of the fusion. So there are the key areas where we say why fusion. This you might all know, in our sun we have this, or in all our stars, the fusion is actually occurring naturally, and this is what we were trying to do on planet Earth. So whatever current energy we are receiving is basically the transformation of this fusion which is already occurring in the stars, and the light energy which we are receiving on planet, we are converting into different forms of energy. So there is always a decrement. So why not try to get the real one? So that's the quest. To do that, we do a little bit of physics. We try to fuse a small isotopes of hydrogen, deuterium and tritium, which gives us an energy, and a neutron, which is important. Why? We see later. And to do so, there are similar things, what is happening in space and what we are trying to do it here. We need higher temperature, which are there in space already, millions of degrees Celsius. So we need to have this temperature. Second thing, in space, we have a gravitational force, which is guiding all of these stars and sun together in one singular form. So that we need to have to recreate here on Earth. And to do so, we created the ITER. ITER is a big machine, a big collaborative project with 35 nations working together and being under construction at south of France in Cadarache. We have 5 major objectives. First, to have this high temperature deuterium tritium burning plasma, means a self-sustaining plasma that you need not to keep on giving energy to have the fusion, but it will automatically be happening. And we'll be having a big 800 cubic meters of plasma volume for that. And to generate 500 megawatt of fusion power in its plasma. So this fusion energy will be coming out of the fusion reactions. And to demonstrate the first of a kind integrated operation of a fusion power plant. So we are actually creating a big scale test facility, which is like the 500 megawatt fusion power plant. Of course, we are not producing the electricity, but we are producing the power, and then to have different experiment and understanding in operations and maintenance. Also to demonstrate the closed fuel cycle. So as I mentioned, deuterium and tritium are the fuels which will be using it for the fusion reaction, and we want to retrieve all this tritium in the closed fuel cycle, so that in a commercial power plant you need not to buy it from external source. You can automatically generate it. Last but not the least, to demonstrate the safety characteristic of a fusion power plant. So today we all know about the safety characteristics of a fusion power plant, how we can take care of the accident scenario, the deviation, even the severe accident scenarios. But we don't know how the fusion will behave in an integral plant size scenario. So we want to demonstrate that as well. So these are the 5 major ITER objectives we want to test. So this is the uh, bird eye view or top view from of the site, which you can see. This is where we are in the center of this building, the reactor, and they are all supporting buildings which are supplying the necessary supply for cryogenics, for power, electrical power, heat rejection, and all of it. How it works. So basically, you inject some gases into the machine, you heat it at plasma, and you reach 250 million degrees Celsius, and you get fusion. Simple. Not a big thing. The problem is how we contain it, how we keep it in that temperature and within that location. So for that, what we do, we use a big network of magnets. We have 3 different types of magnets, the poloidal field, toroidal field, and a central solenoid, which all together gives you a strong magnetic field of close to 40 Tesla, which is one of the highest in the world. And we use that to contain all the plasma in the systems. So we have this sort of toroidal field magnets, which is giving close to 12 Tesla. These are 18 in numbers. We have this sort of a circular ring type of poloidal field magnets, which are fabricated by Fusion for Energy for us. We have a colleague with us. And they are 6 in numbers. And we have a central solenoid being fabricated by the US, and it gives you close to 14 Tesla of magnetic field. So all these together, they create a helical circular plasma magnetic field, so to have a high density plasma, and it's easy to get the fusion recipe. To power all those systems, we have the big power supply already on site, installed and operating. We have a biggest cryogenic plant in the world at the site, already pre-commissioning. We have a biggest refrigerator on the planet. We have a 30-meter high cryostat, where all this cryogenics will be kept in, and an entire machine will be kept inside. It is being fabricated by Larsen and Toubro in India, and it is already completed in 4 different sections, and it was one of the toughest example of welding, the fusion grade welding. Key components. So now we have the cryostat, where we can create your cryogenic temperatures for operating the magnets. We have the vacuum vessel, which is being fabricated in 9 sections because it's like a donut. We create 9 sections already and then fuse it together. We have a network of magnetic fields, which gives you the entire system. We have blankets, which shields the inner temperature and inner plasma temperature within the vessel, and also try to maintain all those radiations within the vessel. And they also help behind these shielding panels. We have a cooling network to take out all this fusion energy. And we have a diverter. So when we shut down, and we also try to shape the plasma to remove all these disruptions and stable plasma. So again, how it works, you simply put the gas inside this, you create the plasma, you heat it up with different type of radiations, magnetic microwave radiations or neutral beam and all of it, and you reach to the plasma temperatures of 150 degrees Celsius, which is 10 times the temperature of the sun, and you get the fusion. And as I mentioned, we are not creating electricity out of it, so we cool down the entire energy using a big network of cooling power system we have, and we have a capacity of 1200 megawatt of cooling power network. Considering the closed fuel cycle, we are testing 4 different technologies of tritium breeding blanket system, which will help in future commercial systems. It will take out the heat as well as recreate the tritium for the closed fuel cycle. So 4 different technologies from 4 different countries: Europe, Korea, China, and Japan. 2 water-cooled and 2 helium-cooled to have this future-ready plant technology. We have a big collaboration. So all these big components are being fabricated in different parts of the world and being transported especially created manner by Daher, our partner here, who bring all those components on site. And there is a dedicated path created in south of France for that. And we have already assembled we are in the phase of assembly. We already lowered the cryostat base. And recently we came up with the biggest thing, the challenge of a first of a kind components. So all these components are super large in size and being fabricated first time in the world. So we are also experiencing some different type of challenges which we came to know. Recently we came to know that there are some non-conformities in our vacuum vessel sectors. So we are making a repair of it. We also found there were some leakage possibilities due to the stress corrosion in the thermal shields. So some of them are being repaired and some of them are being newly fabricating process. So because of these reasons, we are considering the baseline or the deadlines or the timeline. We are in this phase and we are creating a proposal for that. So in next year, June, we will be proposing a new timeline to ITER Council, and we will have the versions later on. So in addition, we are also working on training and mentoring programs, as well as sharing the knowledge with the other countries and other people. And ITER came up with the Infused initiative, the International Fusion Education Initiative, to collaborate with all different kind of organizations, research institutions, and university across the globe. And we are also targeting to bridge the knowledge gap as well as gender gap. So Indian Youth Nuclear Society is working closely with ITER organization to bring the outreach possibility to all the young professionals globally. And we have launched Women in Fusion initiative to bridge the gender gap within fusion community, because it is more of a niche topic right now. So thank you for now. I'll invite Mac for the procurement things. Thank you.
Hello. So my name is Max Stanley. I'm the recently appointed head of procurement at ITER. Okay, a little closer. Can you hear me? Okay, that's better. So my name is Max Stanley. I'm the new head of procurement at ITER. I've been there for about 2 months now. It's a fascinating project, as he just described, but in terms of procurement, there's a lot of opportunities. He showed a lot of delivered components, but there's still a lot to be delivered. So as he mentioned, it's 7 different nations coming together to build this plant. But of those 7 different nations, each one has its own domestic agency. It's important to note that, because in terms of procurement opportunities, it's not only the ITER organization here in France. You can pursue procurement opportunities with all of the domestic agencies as well as the ITER organization. So what this slide shows, this is a very important slide. This is essentially the supply chain's roadmap to how to get into the contracting with ITER. So you can see the specific systems, like here you have cooling system, cooling water system. It has an Indian flag as well as American flag, because the scope is divided across all the domestic agencies with assembly executed by the ITER organization. So you could look at this slide as a roadmap, see where your specific industry overlays, and then go to that domestic agency's site to pursue opportunities. It sounds rather complex, but I tried this yesterday just to see if it worked. You can actually Google each of the domestic agencies and get to their tendering opportunities within only 3 or 4 clicks. It's far easier than I actually thought it would be, but it's working quite well. You've seen this before. One thing to note here, civil works may be 80% complete, and most plant systems are in commissioning, but as you can imagine, if it's in commissioning now, the entire site is not going to be complete for a while, especially after the rebaseline that was just discussed. So some of the systems that are already set up, there's maintenance opportunities, possible refurbishment opportunities. There's still quite a bit of opportunities within those systems. So the split across the DAs, you have the European domestic agency that is responsible for 45% of the scope. The other domestic agencies are responsible for 9%. I think it's 9.2 if you're trying to do the math. One more thing. When you're pursuing opportunities with each of these domestic agencies, it's very important to note that each domestic agency's procurement and tender process is subject to their own rules and regulations for public procurements. The ITER organization is governed by international rules. So it's not a problem, it's just something you should keep in mind as you're pursuing tendering opportunities with each of the agencies. There can be different rules and regulations depending on which agency you're working with. I discussed this part already. Okay, so for here, this is the ITER.org website. This is how you can access the tenders directly for the ITER organization. It's very important to know that in order to work with the ITER organization, you do need to be registered in our Ariba system. There are already over 1,000 suppliers that are successfully registered, but I would encourage all of you, if you're interested in pursuing opportunities, become registered now. Don't wait until you see a tender opportunity that you want to pursue, and then maybe there could be a time hurdle to submitting your tender. Let's see. There's 1,000. Oh, I'm getting ahead of myself. My apologies. Okay, so now we'll touch on some of the key highlights coming up. But as was mentioned before, we are about to go through a rebaseline exercise. And the full impacts of that rebaseline on procurement schedules is not yet known. We're working with project controls to figure that out. But what's going to be very important as we go through this is to look at the website, and we know that communication is going to be key with the supply chain. So we will keep the website up to date with the best schedules that we have at the time. The plan for 24 is agreed, and 24 is when we plan to go through rebaseline. So there is a known schedule for the next 12 months. It's after that for 25 and onwards that's still a bit in flux right now. So, tokamak cooling water systems. If you remember the slide before, the roadmap that I discussed, that one is listed as scope from the United States DA, but that one has actually been transferred to the ITER organization here in France. So there are some times when scope transfers back to the ITER organization. TCWS is one of those systems. Heating current drive will be coming up in the first half of 24. Also cryostat and some of the common feed-through supplies. Operation and control systems, lots of instrumentation and control. With ITER being more of a science experiment than a power plant, diagnostics and instrumentation is absolutely essential. That's really what we're after here. It's not the power to put into the grid, it's the data so that we can help others put the power into the grid. Civil works, again, the earlier slide said civil works are 80% complete. As typical with any construction project of this size and complexity, there's a lot of changes. So that remaining 20% will also couple on a lot of integration with delivered systems. And from the European DA, F4E, we have someone here as well, Benjamin. I can turn it over to you to discuss specific EU opportunities as well. Thank you.
Okay. Thank you very much. Thank you, Mac. Not sure how I can put that. That one, yeah? Yeah. So just a couple of messages from our side. So I'm representing the European Domestic Agency for the ITER project. So we are in charge of delivering the components on which Europe is committed, which is basically 45% of the machine. Just to comment that Fusion for Energy is not only engaged in ITER, but we have some other fusion-related devices that we are working on at the moment. It's important. ITER is not a one-shot. There are other topics which should culminate with the start of the fabrication of the demo reactor that will be connected to the grid. These are the components on which Europe is engaged in ITER. So important to note that Europe, having 45%, is engaged in almost all the technological and strategic items in order to make a fusion device operate. So here you can see the big components that we started to manufacture in 2008, the magnets, the vessel, and some of the in-vessel components. But we are now starting to go into the more specific systems, the diagnostic system, some of the heating system like EC launchers, the neutral beam heating system, cryopumps, and remote handling. And of course, the test blanket modules, I will come back on this. In order to understand more how we work and what we do, we have a little group. I'm here with my colleague Mehdi Daval. So you have here the contacts and the industry portal address where you can get some information on upcoming business opportunities and also on the ongoing call for tenders. Okay, some examples now of what comes next in terms of business opportunity. I was mentioning the TBMs. So the TBMs will be key for a fusion operation. And the TBM are here to test and validate during the operation of the ITER machine the tritium breeding blanket concept that will be used in future fusion reactors. We will have 4 of these test blanket modules. And ITER will test some of the concept in order to have this up and running for fusion devices. And for this, we will start next year to procure some of the ancillary system. So if you are interested in that, note that we will launch a market survey on these 3 first systems, tritium extraction system, accountancy, and glove boxes in tritium room. So these are the examples to show that from the big components, the vacuum vessel, the magnet, etc., we are now entering in more specific components. In remote handling, many things to come too in the next years. We will have a first big contract for the design, prototyping, and manufacturing of some of the remote handling system for the machine assembly phase 1. It will cover the divertor remote handling system, the cask and plug remote handling system, and the neutral beam remote handling system. So this will come in 2024. These are only examples. I'm rushing a little bit because I don't want the next one to be too late. We have also some activities around the divertor. So the divertor is the lower part of the tokamak. And we will have also some activities in there in the coming years. In the cryoplant and fuel cycle, we will procure some additional cryopumps. We will have a call for tender in 2025 for this. Other important system, very important system, I know there are interest here in this supply chain around radiological and environmental monitoring system. This will come later, but of course we are already starting to identify interest among industry. And to finish, I would like to mention on the heating system, we have lots of mechanical and assembly objects to be manufactured. The passive magnetic shielding, it's an important scope of activity for us. We are looking at companies able to as very often in what we need to buy, to be able to perform high precision machining and assembly with very tight tolerances, and able to move heavy components with a lot of precision under nuclear codes, of course. So these are only examples of also the drift duct that we are going to procure. The call for tender is planned for next year. I think there is a bug here with the picture. That's a shame, but we will share probably the presentation and diagnostics. So that's it. In any case, any question, we will be in the room behind, and we are happy to discuss with you now. Thank you. Have a good day.